Welcome to this first video of my playlist about the best methods for reducing carboxylic esters to primary alcohols. This is a useful synthetic transformation because many structurally diverse esters are available and primary alcohols are also valuable synthetic intermediates. If an aldehyde is required, one common strategy is to reduce an ester to the alcohol and then oxidize it, for instance by Swern oxidation. Both transformations proceed in high yield and are often superior to the one-step conversion of an ester into an aldehyde. In this video we'll have a look at catalytic hydrogenations. This is the most inexpensive and environmentally friendly method, but often requires high pressure and lengthy optimization. For small-scale preparations, other strategies are usually preferred, such as those presented in parts 2 to 4. Reductions with alkali and second-group metals, such as the Bouveault-Blanc reduction, are discussed in part 2. These also usually require some optimization. The most straightforward strategies are reductions with boron and aluminum hydrides, which are presented in parts 3 and 4. These reagents are, however, expensive and generate a lot of waste, and are less suitable for large-scale industrial reductions. In my channel you can also find a video playlist about the reduction of carboxylic acids to primary alcohols. Because esters are easier to purify by chromatography, for small-scale laboratory preparations the reduction of esters is more common than that of carboxylic acids. With most reducing agents, esters are also easier to reduce than acids. The latter may also consume one additional equivalent of hydride by protonation. One industrial use of ester reduction is the preparation of fatty alcohols from triacylglycerides. Fatty methyl esters are first prepared by trans-esterification of triacylglycerides and then hydrogenated at high pressure and temperature with a heterogeneous catalyst. These usually consist of copper, chromium and zinc oxides. Noble metal catalysts based on palladium or platinum are less well suited for the hydrogenation of carbonyl groups. If primary alcohols are thermally stable, these can often be prepared by heterogeneous catalytic hydrogenation. In this example, a branched nonanol was obtained in high yield by hydrogenating a methyl ester at 200 degrees Celsius for 20 hours. An inexpensive supported copper-chromium catalyst was used, without any additional solvent. Few laboratories have equipment to perform hydrogenations at 200 degrees Celsius and 200 bar. Therefore, catalysts that work under milder hydrogenation conditions were intensely sought after for many years. A number of soluble catalysts are known that can bring about ester hydrogenations at more moderate temperature and pressure, but often some alkoxide or other co-catalysts are needed. In this example, 10% of a copper-carbene complex, together with a slight excess of a crown ether and sodium terzbutoxide, catalyzed the hydrogenation of an ethyl benzoate. No benzylic CO bond cleavage or hydrogenation of the arenes or the alkene occurred. With only 1% of a cobalt-carbene complex and 5% of potassium terzbutoxide, the starting ester of this example could also be hydrogenated, again with high selectivity and under mild conditions. Many homogeneous catalysts suitable for ester hydrogenation contain aminoalkyl phosphines as ligands. This is unfortunate because these phosphines are not readily available and difficult to prepare. In this example, 0.1% of a manganese complex with such an aminophosphine was used to hydrogenate substituted methyl benzoates. Even a thioether and an aryl iodide could be hydrogenated in acceptable yield and under mild conditions. Again, no benzylic CO bond cleavage occurred. Here, oleic acid methyl ester was hydrogenated with a structurally simpler aminophosphine manganese complex. A high yield of the unsaturated primary alcohol was obtained. A large number of ruthenium complexes with aminophosphine ligands have been used as catalysts for ester hydrogenations. This here is an optimized example of the hydrogenation of methyl lactate. Because ester hydrogenations often require an alkoxide co-catalyst, racemization was one potential issue. With only 1% of sodium methoxide, however, almost no racemization occurred. A high yield of propanediol was obtained after hydrogenating for 12 hours at only 28 degrees Celsius. In this example, a ruthenium-carbene complex was used as catalyst, again with an aminophosphine ligand. Despite the high reactivity of naphthalenes, no arene hydrogenation or carbon-bromine bond cleavage occurred. Only 4 bar of hydrogen was sufficient to attain a complete hydrogenation after 4 hours. In this example, protected methylprolinate was hydrogenated with a ruthenium complex devoid of aminophosphine. Instead, a mixed diamine-diphosphine complex was used. No alkoxide was required and the conditions were sufficiently mild to prevent deprotection or racemization. Here, an enantiomerically pure aminophosphine ruthenium complex catalyzed the hydrogenation of an aryl iodide containing ester without any carbon-iodine bond cleavage. Moreover, one of the 2 enantiomers of the racemic starting ester was hydrogenated faster than the other enantiomer. Because the sodium ethoxide caused the steady racemization of the starting ester, but not of the product, an enantiomerically enriched product was obtained. In this example, a ketoester was hydrogenated enantioselectively with an iridium aminophosphine complex. No benzylic CO bond cleavage or dechlorination of the arene occurred, and an exceedingly high enantioselectivity was achieved. The hydrogenation conditions were mild and only 0.1% of the expensive catalyst was required. Let's have a look at some potential side reactions. Because of the alkaline reaction conditions, trans-esterifications can readily occur, also of the starting ester with the product. If the resulting new esters are sterically demanding, this may slow down the hydrogenation and consume part of the product. Then, treatment of enolizable esters with alkoxides can promote Claisen condensations. Occasionally, aldehydes may result as byproducts. When hydrogenating lactones, for instance, the intermediate hemiacetal may not release the aldehyde quickly enough, and the main product can be the cyclic hemiacetal. If the resulting alcohol forms stabilized carbocations or readily eliminates water, products of overhydrogenation may result. In this example, hydrogenation of a benzoate yielded a toluene instead of the expected benzylic alcohol. Similarly, the newly formed alcohol may undergo etherification if the hydrogenation temperature is too high, as in this example. Even a small amount of butanol was formed by reductive CO bond cleavage. Here are some further examples. You can also copy these references from the description of this video. The next video of this playlist is about the reduction of esters with metals of the first and second group. These reductions are inexpensive but not very selective and may require some optimization. See you then.